All right. So good morning. Thanks for attending this talk. This talk is actually about lab automation, right? So who really cares about lab automation? Why, if you're here and you are an engineer and you're working in labs, you're responsible for rolling out new services, and you're constantly scrambling to patch and manually move cables and equipment in labs, then you probably have a problem that through lab automation can be addressed and resolved. Really, the business driver for lab automation is the ability to accelerate testing and onboarding of new services, building dynamically network topologies without having to patch manually, which is error-prone and definitely time-consuming. Another huge problem in labs is also equipment sharing. Typically, very expensive traffic generators are siloed in different groups or organizations, and sharing this equipment is actually complex and difficult. Typically does not happen. That's why actually lab automation is relevant, really to increase the velocity and reduce capital expense and overall cut operational cost in lab environment. So I want to first review the basic concept of layer 1 switching. I'm sure everyone is familiar with it, but just to level set, a layer 1 switch effectively operates as a software-controlled patch panel. Once you can connect your routers or switches or traffic generators to a layer 1 switch, and the layer 1 switch effectively allows you to create circuits which can be dynamically modified through software, effectively a software-controlled patch panel. And to do that today, there are actually numerous technologies. Here I list the three most popular, but actually there are more technologies. There are packet brokers, derivative technologies. There are optical cross-connect, and there are media and optical media cross-connect, which also deals with electrical and optical interfaces. Overall, they do the job. Nothing wrong with any of this technology. However, you will find out as you actually try to implement this technology, the flexibility is not there. The ability to actually perform, operate in an environment with high availability, resiliency, also the ability to perform what I call here the DUT circuit sharing, or ability to effectively to, here, DUT circuit sharing, the ability to actually leverage multiple channels across, or a single channels across multiple DUTs, and even extend the layer 1 connection across labs or layer 3 networks, or even labs at different floors is actually not there. Those are typically chassis-based solutions built on custom technology, sometimes also very, very expensive. So what can we really do to improve the situation here? Another point that I want to make is that if you actually look at the technology commercially available from a layer 1 switching point of view, they really have a hard time to keep up with the explosion of Ethernet PMDs and PHYs and PMDs and the diversity of multi-mode fiber, single-mode fiber, copper, direct attach, multi-lane, single-lane. Very difficult to find this flexibility into an optical cross-connect, a layer 1 cross-connect, or even a packet broker. One thing we can do to actually start to change and improve on layer 1 switching technology is actually see if we can use whitebox, traditional whitebox technology. Those are commodity switches which operate, of course, their job is not to perform layer 1 switching, but perhaps we can emulate a layer 1 switching with a whitebox. If we do that, just because we use this hardware, immediately we get all the flexibility in Ethernet interfaces. From 1 gig to 200 gig, 400 gig, 100 gig, immediately you get the benefit of having a platform which scales nicely, effectively with your network, because effectively it's the same device you can use in your network. We have full ability to convert a single mode fiber connection into multi-mode fiber, copper into fiber, mix and match all this connection, and even speeds. You can connect a 1 gig port to a 100 gig port and still have effectively layer 1 emulated connectivity. Because these white boxes are normally 1U, 2U at the most, you can actually build a very large scale-out fabric through leaf and spine architecture, and you can accomplish, let's say, scale capacities which are at least an order of magnitude higher than a traditional layer 1 solution. I'll show you a couple of examples in a moment. And while you do all that, you can dramatically reduce the cost of building a layer 1 switching fabric for your lab compared to traditional technologies. So I want to show you now the most interesting part. Yeah, the white box is interesting. It's actually very powerful in terms of hardware platform, but there is software that can also take advantage of this platform and perform what I call it a layer 1 emulation. Of course, you're dealing with a packet switch platform, and you're trying to emulate a circuit switch technology. I call it here for simplicity virtual wire, because effectively we're not really pulling wires like you do in a physical, let's say, cross connect or in a physical layer 1 cross connect. What we're doing here, we're emulating virtual wire. And I'm going to propose two approaches. One is extremely simple. One is more complicated in terms of implementation, but it's a lot more flexible and frankly a lot more interesting and exciting when it comes to building a next generation lab automation. So one is based on the white box hardware. I'll show you how it can be done. And the other is based actually on an IP plus an overlay type of technology. So you end up encapsulating all your DUT device under testing traffic on top of an IP overlay with some interesting properties. Let me walk you through the first example, the first scenario, using a basic white box. And then what you do here is actually pretty simple. This is let's say, a sample pipeline of an ASIC, a merchant silicon chipset. You have your tunnel termination, your layer 2, layer 3 lookup. You typically have an ingress ACL tables. You have a metering functionality, buffering, et cetera, egress ACL. This is the full pipeline. The trick here to emulate a circuit switch using a packet-based technology is to disable most of these blocks. So the software is supposed to turn off most of these processing blocks in the pipeline of the packet. So what we do in the software, we need to disable number one, MAC learning. Second, you want to disable any layer 3 routing and switching BPDU kind of processing. On top of it, you need to prevent the CPU of your switch to receive any packet from the network. So the entire control plane processing needs to be turned off. And all the switch is supposed to do is program for port 3 to be connected to port 10, is to program effectively an ingress ACL. And this ingress ACL has a very simple rule which says associate all the traffic coming from port 3 to port 10. And because you have disabled all the rest of the processing, you effectively have already emulated a layer 1 switch. It's a nifty trick which allows you actually to use a white box as a true, let's say, as a quasi layer 1 switch. Of course, there are limitations which I'm going to discuss later on, but at a high level, this covers probably 95% of the use cases. Also, I want to point out that at least the devices we experimented with allows you actually to turn off error frame processing. So you can actually transport CRC error frames, Ethernet frames. You can also transport RAN packets, small packets. So you can really emulate a true wire in terms of transparency even to packet errors. And last but not least, I want to point out something interesting, because this is what actually layer 1 switches do. When port 3 goes down because you disconnect the DUT, you are supposed to send a signal to port 10, and port 10 gets disconnected. That's what happens when you open a circuit. Well, in this case, your software the software running on this white box needs actually to perform this operation of effectively propagating a link failure or a link up-down event to the remote port. So this is a couple of examples of what you can achieve with this. You can achieve full transparency to any Ethernet packets. You have error frames at the top, control packets at the bottom. You can have LLDP packets, BGP, LACP, and different ether types, even MPLS, fiber channel over Ethernet, all sorts of encapsulation ether types actually can transport it across an infrastructure program the way I described before. Also very interestingly, from a flexibility point of view, you can actually have a 100 gig port, talk to a 10 gig port, a fiber connected to a copper. All these combinations are now possible, and many of those things are not possible actually with traditional layer 1 cross connects. This is an example you can build easily with 1U switches, with a 1U switch with 32 ports of 100 gig, which splits into, each port splits into 4x10 or 4x25. You can easily build a non-blocking fabric with 2048 ports with 16 spines and 32 leaf switches. So the scalability is actually pretty significant. Just want to show this as an example. So in a nutshell, what do you get if you use a white box with a few tricks in software to emulate a layer 1 switch? What you get is a device which is transparent to all kinds of Ethernet traffic, encapsulation, including errors. You get a device which gives you enormous flexibility in terms of mix and matching Ethernet interfaces, any speed, any media conversion. If you're lucky, you get an OS that implements the logic to track effectively the state of a port across the fabric. So you can disconnect on leaf 1 the DOT that is connected to leaf 25, and leaf 25 is supposed to receive a signal that this device, the device has to be disconnected, or there's a link up and link down event. This infrastructure is normally programmable, unlike traditional layer 1 switching. You can use modern REST API, Ansible-style automation to actually program this kind of infrastructure. And you also